For robots to operate in the real world, they can't just be stationary arms. They need to be mobile manipulators. But coordinating a mobile base and a robotic arm simultaneously, what we call whole-body motion, is incredibly difficult. The state space grows combinatorially with every new object or scene, and finding physically valid paths in that space is like finding a needle in a haystack. The industry has hit a wall. Teleoperation is too slow and labor-intensive to scale. Reinforcement learning in simulation often suffers from massive symptoreal gaps. And traditional motion planning, while precise, it's computationally expensive. Until now, we've had to choose between scale, diversity, or kinematic fidelity. You couldn't have all three. Enter AutoMoMa. AutoMoMa is a GPU-accelerated framework designed to break this bottleneck. It allows us to synthesize over 500,000 physically valid, coordinated trajectories across 330 diverse scenes and multiple robot embodiments. To put the speed into perspective, AutoMoMa generates 5,000 episodes per GPU hour. That is 80 times faster than previous CPU-based baselines. But how does it actually achieve this? The secret lies in a method called Augmented Kinematic Representation, or AKR. In a standard setup, a robot and the object it's interacting with are treated as separate kinematic trees. AKR changes that. It unifies the mobile base, the manipulator, and the target object into a single, continuous serial kinematic chain. To do this, the system takes the robots and the object's URDF files and performs a kinematic inversion. It effectively reroutes the object's model at the grasp point and attaches it to the robot's end effector via a virtual joint. We also introduce a virtual base to model the mobile base's planar motion using prismatic and revolute joints. By treating the entire system as one chain, we can optimize the movement of the base, the arm, and the object simultaneously within a single configuration space. The AutoMoMa pipeline then moves through 4 distinct stages. First, task specification. We define the scene, the object, which can be rigid or articulated, and the robot embodiment. The framework is embodiment agnostic, meaning it works across different platforms, from a Franca arm on a Summit base to the Tiago manipulator. Second is problem instantiation. To keep the GPU acceleration fast, the environment is converted into a Euclidean sign distance field, or ESDF. We also approximate the complex geometry of the robot and objects using fitted spheres. This allows for incredibly fast parallel collision checking on the GPU. Third is trajectory generation. The system solves a constrained optimization problem to find the smoothest, shortest path that satisfies the task. For example, if you're opening a door, the system enforces a strict pose constraint, so the robot doesn't pull the door off its hinges. For complex tasks in tight spaces, AutoMoMa can even plan for grasp switching, where the robot lets go and regrasps the object to avoid a collision. Finally, the system uses NVIDIA Isaac Sim to render high-fidelity RGBD images and point clouds for every waypoint, creating a rich, multimodal dataset for training. Now the most important question, does this scale actually matter? The researchers tested this by training several state-of-the-art imitation learning policies, including DP3, ACT, and standard diffusion policy. The results were striking. They found that for a single articulated object task, current SOTA methods need tens of thousands of demonstrations just to hit an 80% success rate. When they compared a fixed-base robot to a mobile one, the gap was massive. A fixed-base robot could reach 100% success with fewer than 800 trajectories because its search space is small. But the mobile base policy, dealing with that complex 10-degree of freedom coupling, struggled to hit 70% even with 3,200 trajectories. This proves that the bottleneck in mobile manipulation isn't the algorithms, it's the data. By scaling the number of training scenes from 1 to 30 and increasing the trajectory density, the policies began to generalize to entirely unseen environments. The data provided by AutoMoMa allows the model to move past simple, manifold memorization, where it just remembers a specific path, and actually learn a generalizable strategy for whole-body coordination. To wrap up, AutoMoMa bridges the gap between high-performance motion planning and large-scale imitation learning. By turning the GPU into a trajectory factory, it provides the infrastructure needed to train robots that can actually navigate and interact with the unstructured chaos of the real world.